Hi guys. Okay, so I did an episode 1 here as an intro to this LILYGO T-Deck device. And we found out it is quite a well-designed device and quite interesting. And now we're going to start to have a look at it in more detail, which means we're going to be looking at the schematic and the code in order to make all the bits and pieces work. And as a reminder, there is a Janyang LILYGO T-Deck GitHub site, and you can just go down there and download the zip file. And once you do, you will have when you unzip the zip file, you'll have this T-Deck master file, which has pretty much everything in there that you need to know about the device, although some of the examples and everything are a little bit, I'm not quite sure what you're supposed to do with them, but nevertheless, because I couldn't get them to compile with either Platform IO or with the Arduino IDE, but nevertheless the files in the libraries and so on are all working, so I'll just modify them anyway. In any case, there is a schematic in the T-Deck master, but I made some little edits to them to put some text in there to show what each section is, just a few comments to actually remind me what it's all about. So when we look at it, it's one big sheet of schematic, and it's too small to actually, even if you print it out on one sheet of paper, you can't hardly read it, so we'll have to zoom in on it. But we can show the sections of the thing here. There's a growth socket there that it has on the side. This is the main microcontroller, which is the ESP32 S3. There's a place there for a LoRa radio chip, which I don't have, so we're not going to be looking into that, and nor do I need it. This is a socket for the keyboard, if I remember correctly. The trackball stuff is over here, which interestingly enough has 4 little chips associated with it, which are actually Hall chips for, they must be magnetic or something. We'll have a look at that in a minute. And it has microphones. Now they show 4 microphones, and it can certainly this analog to digital converter over here, which is specifically made for audio, which is actually good because the analog to digital converter on the ESP32 is not good enough really for audio, not for quality audio anyway. So and this chip is, so they've put a proper analog to digital control on there, and it has two microphones connected to it, left and right, and then there is an audio amplifier over here, and there is a USB socket, and there is a USB power sort of socket with a switch, but the actual, and here's the battery charger, and just a few other bits and pieces, with pull-up resistors and MOSFETs and transistors for protection and what have you. A little socket there. There is a coprocessor here, which is an ESP32 C3, which is specifically used for scanning the keyboard, and there's a little socket there for actually accessing that if you wanted to, but we don't have to because it's already pre-programmed for scanning the keyboard, which is a good thing, because if the keyboard was directly connected to our main microcontroller, it would be pretty much basically be scanning the keyboard all the time, and it wouldn't have much time to do anything else. But the ESP-C3 is used to scan the keyboard and send an interrupt to the main microcontroller here when there's a key press. So that is that. It has a TFT LCD display, which is the socket for it over here, and it has a touch interface, and we'll be looking at all those things. So in this episode here, we are going to exercise the analog to digital controller, which is connected over here in the ESP32 for measuring the battery voltage, just to double check that that works. And we're going to be displaying stuff on the LCD, and we're going to interface with the touch interface to make sure that we can find when this display is touched and so on. So if we have a look at some of this stuff here in more detail, we can actually zoom in. First of all, this is the ESP32 S3 WROOM-1, and it has these are the GPIO pins, and it has the names of what these things connect to in different parts of the circuits. For instance, here is the battery ADC GPIO pin 4, and we have, if we look above that, like there's a growth socket, and it uses UART 0TX, UART 0RX, which is coming from those two pins over here. And now they've got these marked as TXD0 and RXD0, and you could probably, in the board file, they probably have those defined, but it is GPIO pins 43 and 44, if I remember correctly, from the actual diagram. In any case, that is what that is. And if we move down below, we find out that the battery ADC pin is connected to this voltage divider here, two 100K resistors, actually 1% resistors, so have some accuracy, I guess. And the battery voltage is actually applied here. So what the ADC is going to be measuring is the half the voltage of the battery, because there's a voltage divider there. And the battery voltage, of course, is going to be usually up to 4.2-ish volts when it is charging or fully charged. And that is more than what the ADC can handle on the ESP32. It can only go up to 3.3 volts. And so some calculations will have to be done with the value that it comes back with. It's supposed to come back with, it's a 12 bits, so it's supposed to come back with 4096 when it is at 3.3 volts. Now internally, the ESP32 has a 1.1 to 1.2 volt voltage reference, and it varies a little bit, so it is not 100% guaranteed that you're going to get 100% accuracy, but you can make some, since we have to calculate anyway, we can make some allowances for that. We can measure the voltage of the battery and see what it comes back with, etc., etc. So this circuit over here actually is a little bit of a protection circuit for the incoming power, which is actually coming from the USB port. This is the on-off switch, and if we look over here, we find out that we have VDD 3.3 volts. In any case, if we go further, this is the actual battery charge circuit, and it has V-bus coming in, which is 5 volts from the USB port, and it then is a typical TP4065B chips is very common. It is a little battery charger chip that converts the 5 volts to whatever voltage is needed to charge the battery, which is connected to this P3. There's a little plug here, and there is an LED that shows that it is charging, but I think it's inside of the, I made a case for it, I don't think you can see it. It's not exposed on the outside, but in any case, this is a very standard sort of battery charge circuit. And zoom out a little bit here, a little bit of protection circuits here for some of the pins that are not that interesting to look at. Of course, there is a keyboard socket over here that is connected to this coprocessor, which is an ESP32C3. There's also some flash RAM on there, which we won't be accessing directly. This is the coprocessor, which is another ESP32, it's a C3, and as you can see, it has rows and columns, and it's connected to that keyboard socket, which is over here. And that, as I said, that coprocessor is also connected to a little. It's got 6 holes on the PCB. There is a you could potentially put a socket on there and access that coprocessor and reprogram it as well, but we're not going to be doing that. If it works, it works, and we don't want to touch that. Trackball is interesting. It has a switch over here which goes to GPIO 0, and that GPIO 0 is actually used when you want to put the thing into programming or boot mode. And when you hold down that switch and push the restart button, then you will find that it goes into a mode where you can upload the code to it, and then you push the start button again, and then it's in it'll boot and it'll run the software you uploaded to it. That trackball is connected, it's got 4 pins connected to ground, it shows there, but what is interesting about it is this is 4 Hall sensor chips that are connected to the trackball, so up, down, left, right, and so on. And if we look at the low current consumption, high sensitivity, CMOS Hall IC operates for alternating magnetic field directions. Anyways, this is what they're using. I do not think we have to access those chips directly ourselves. I expect there will be a library there to access that trackball, but we're not doing that in this episode, so this is as far as we're going to go with that. We will look at that in more detail later, but it is interesting anyway. So then we have microphones. They're showing up to 4 here, but I believe there's only 2 on the board, left and right. And again, these microphones have a datasheet, omnidirectional, top ported analog output, MEMS microphone, high performance reliability, Little chip with 4 little pads underneath that is soldered to the board. Little hole in the top for the sound to get in, picked up by the analog to digital controller, which is this one here, and it is specifically made for audio, which is good because the actual analog to digital controller on the ESP32 is very limited for analog signals. You can use it, but your signal will be of not great quality. So this particular chip here is actually addressed via I2C for its control, commands and so on, but it outputs I2S signals. Typical example here, I don't know how close that is to what we have. That is what this thing is here. That is the ES7210, and as you can see, there's microphones, input, and so on, and it outputs audio, which in turn is picked up by the audio amp, which is a MAX98357A, very common chip. You can even buy those on little breakout boards from Adafruit and so on. And this is what that is: tiny, low-cost PC amp, Class D amplifier with Class AB performance. And so what this is all about is that a Class D amplifier actually outputs like a pulse width modulated signal, which means it is very efficient and it doesn't run hot, doesn't need a heatsink and so on. And when it gets into the audio circuits, you know, like through speakers and so on, it actually gets filtered out and it just becomes an audio signal, and it works very well. So that's what that is all about. And as I said, it's a common chip. You find them available and pretty much anywhere. This is the screen connector, LED backlighting and so on. And driver here for the LEDs, so that the ESP32 doesn't have to drive those directly, because it couldn't anyway. And this is the USB port, which is actually a standard USB 3. It is a USB-C socket, but it's a USB 3 implementation. And as we saw before, there is the battery charge circuit. I think that's pretty much it. Okay, so here we are in Visual Studio Code, and we have the PIO Arduino extension loaded. PIO Arduino is an extension that you can actually find under extensions. That is actually a fork of the platform IO, with the only difference is that it uses a slightly newer library that comes from the ESP32 people, which means that you can use the latest processors like ESP32P and H and whatever else they've got. In any case, that is why it doesn't have that little alien face there, but the rest of it is still all platform IO based. So let's recoup a few things from that we also discussed in some previous videos and in the last episode. And that is that if we look at platform IO ini here, you will notice a couple of things here. Now, this platform IO ini file was actually based on one that I actually copied from the code that was coming from the GitHub site. And as I explained last time, some of this stuff there, I didn't type in myself. I got it from there, but I did remove some stuff, and I commented out this T keyboard stuff, which we don't need. But the rest I've left in place. But I did add this build flags thing to it, which we'll discuss in a second. So the first thing, the only general library we need is this BODMA TFT ESPI library for accessing and displaying information on the liquid crystal TFT display. And of course, how you can do that is you can go to PIO Arduino, and then under PIO home you see open, and you can click that. It goes to the PIO home file, and you can find libraries there, and you can put TFT underline ESPI, and there it is there. You could click on it and say add to project, and of course I've already done that. So, and if you do, you will find that it will then have added this line to your platform IO ini file. Now, when you do that, if you look under the PIO folder here, normally it's like this, but if you open that up, you'll find that now it has a new T-Deck thing on the libtabs as well. And if you look in there, there's TFT ESPI, that is what we just loaded. And as part of that, there is this user setup H file. Now, the thing that you normally have to do after loading up this TFT library, ESPI library, is you have to edit the setup H file in order to reflect the settings that you need for your particular display. and so it is actually an ST7789 driver, and there's a bunch of settings and so on that you uncomment, and you comment some out and so on in order to get the right values. Now, if you're using an Arduino IDE, this stuff is located in the library folder, which is usually under your user ID, Arduino libraries and what have you. But the only problem with it is that if you ever update that library, then it will overwrite the setup H file and you will lose all the settings you've made. You have to do it again. So luckily in platform I/O based systems, we can actually put those very defines in the actual build flags section of the platform I/O ini file. And the first thing that you will then do is anything with a -d in front of it is like same as a hash define in the code files, so in H file. So the first thing you do is you say user setup loaded, which signals to the system that the user setup H file is not going to be read. The library realizes that the defines have already been done that way, and we can then define all our defines nicely here. The ST7789 driver, the RGB order, this is BGR, and so on. The only slight anomaly here is, and I don't know why that is, I might investigate that further at some stage, but you would think that the width of the thing is actually 340 and the height is 240, but in actual fact it doesn't work properly. I had to set the width to 240 and the height to 340. So I don't know if the display is actually meant to be used in vertical mode and that's why, or what the reason for it is. But in any case, if you swap the height and the width for what you might originally think that it is, it works perfectly. So I haven't looked into that any further. Now, another thing to notice is that with this TFT library, it can now normally handle touch for you, and you see this commented out line here. If this is defined and you give it the touch CS file, then it will include a touch section in the actual TFT ESPI libraries, and you can there are some samples there that is provided by the author of that TFT library, but that does not work for our T-Deck on account that it is structured differently. So I'll show you what I mean. So this is the display on here. Now, if you get a general purpose display like this one here, which you would normally hook up to your ESP32 or your microcontroller, whatever you have, you notice that it is a 3.2 inch TFT SPI 240 by 320 capacitive touch. So, but it is actually different. If you look at it closely, you will see that it has additional pins here for, this is, that's the best way you can see it, CTP, INT, CTP, STA, CTP, RST, reset, STP, SCL, and you can actually hook those pins up in order for the touch, and these pins here are used for the actual LCD display. So in that case, you can use the TFT library to you would connect the the SPI pins, you would connect them to the same bus, and it actually works. But we don't have that available here, and in actual fact, I went into the code that LILYGO provided. All right, so there's actually a chip on the little T-Deck display board that actually handles the touch. And as you can see, it's a GT911 5-point capacitive touch controller. And It's just a chip you might come across, block diagram, but we don't actually have to address this chip ourselves, because the LILYGO people have actually supplied the library files for us to do that. So what I did was I went into the examples, and there is a touchpad, and there is touchpad inno file, which I can open up here, and as you can see, there's a touch drive GT911 HPP. That's the starting point for it. And if you then drill down into that file, you find there's other includes and so on. And these guys are actually all located in the lib folder, and sensor lib, and source, and you'll find, you see there is there it is here, touch drive 911 HPP, and then of course when you open that file up, you'll find that it includes other files, GT911 constants, touch drive interface HPP, sensor common TPP, and you'll find all these files in, you see there's some are in there, in that red folder and so on. In any case, I've found them all, and if you download the code, you know, from my website, you won't even have to find them yourself. They will be included with the sample code. But in any case, that is where they are from. And if you look at the source code over here, you'll find in the include folder, indeed, there's all these files there. You see GT911 constant.h, sensor common TPP, sensor libh, and touch drive GT911 HPP, touch drive interface HPP. So these are all the files that I got from the LILYGO files that were downloaded from GitHub. The only things I created myself was T-Deck devs and TF utils and touch HPP, just those three over there. So if again you look at the files in here and you look at the examples, you'll find that all the examples have this utilities H file, and they have, you know, board something, and it's not very clear what these things should be used for. And that is where the file that I created comes in, the T-Deck devs. These are the same values, but I've renamed them. Instead of board, it says T-Deck, and I've grouped them into the bits into groups of what they're used for. So, you know, these are speakers. I've renamed some of them actually to T-Deck speaker, power on. These are I2C keyboard and touch interface, battery, ADC, TFT, backlight, TFT CS and DC. That's for the screen, obviously. And then there is the SD card, trackball, and microphone. And we are not actually using those yet. That's for future episodes when we're going to do audio and trackball and keyboard and all that kind of stuff. So that's what I did. That takes the place of that utils that they have. And then in your main file, in your main code, you actually don't want to have all those includes and things included, because we want to create libraries and modules for ourselves that we can include in new projects. If you want to do a serious new project, you don't want to have to copy and paste all those includes and things, so you create new modules. Now, the best way to do that usually is to create a class of your own, which is what I did for the touch one. See, class touch, and it has in there, it calls the class that the LILYGO people provided. It's encapsulated in there, as you can see under protected, touch drive GT911, and because no one needs to access that, they can access stuff from our class, so we can pre-digest it if you like. And right now it has an init. It comes back with is touch, with the number of touch points that it has stored, and then you can get the X and the Y coordinates of the touch, and there's some stuff here maybe that might be used in the future. Get pressure, get status. There's another include module, another class that can be included that actually then brings out some additional information on the touch point, but I don't need that. I just need to know when something is touched and where it is. So I put it in there, but I commented it out because I don't need it. Maybe we'll need it in the future. In any case, so that's one way to encapsulate, libraries and things like that. So, and then all you have to do in your code is just have one touch HPP. Now, another way you can do that is you can actually create a module that just has functions in it, which is not a class, but you can have a whole bunch of defines in there and local variables and so on, which you don't have to declare in your own code. As I said, the aim is to move as much of the general purpose code to a different place so that you can just include one line as an include statement and everything is there. So these are all the functions that, or some of the functions are created to access and display stuff on that LCD. You can erase a portion of it, you can clear the screen, you can show something at the center of it, you can show a line just like you do with the serial monitor. You can, it says print line, but here it's got show line, and you can check out where the cursor is, and you can set a different text mode and so on. You set the brightness, and you can set up the TFT. Now in this case here, I actually return a pointer to the actual TFT ESPI class, and I'm not actually using it, but you can see that's happening here. TFT ESPI is a pointer to it, and then over here during the setup, I just say TFT equals setup TFT, and it of course returns that pointer. So if I ever do have to access something low level in the TFT class, I could still do it. But that's what I did there as an example of how you can encapsulate different code and reuse it in other places. So, and as far as the main file is concerned, we are testing the analog read on the battery ADC. We are actually wanting to show that we can display stuff on it, and we want to be able to use the touch information to see where the screen was touched. So there's the three things that we're doing in this episode. And in order to do that, we got a bunch of pin modes to set. Touch interrupt is input. Digital write power on is high. You got that's the main power on for the board. The battery ADC, of course, is an input. And then there is the TFT LCD screen, backlight, and chip select. Output, chip select to be high, so the screen is on. Set the brightness to 15, which is the maximum. And then we set a text mode, and we clear the screen and show something in the center, initializing for a second. I found out that when the first time you do the read battery voltage, which is actually this little function over here, it comes back with an invalid value. I don't know why. Or maybe it needs a little time to settle down or something. Who knows? But 1 second seems to be enough. So I actually delay for a second, and then all's well. And then we initialize the T-Deck Touch library, and we'll display a message if it failed. Clear the screen, and then over here we have this is our class, T-Deck Touch. If it is touched, then we can display a little asterisk at the place it was touched. and then we go and if it is less than 10 and less than 10 on X and Y, we added a little feature here to actually clear the screen. So if you touch the screen right at the top left corner, it should clear it. And that's it. It's very simple. Do note too that it has a delay of 100 milliseconds. That's why, as you will see, when you move the stylus over the screen fast enough, there'll be gaps between the asterisk. But if you move it slowly, it is almost like connected. Now, that tells you that in a real application, you'll probably, under certain circumstances, if you are, let's say you're creating a little drawing application, this wouldn't be good because you wouldn't want to have a delay in it then. And in fact, the ESP32, I believe it has 2 cores, if I'm not mistaken. In any case, at the very least, you would have to either put some code in a separate core in order to scan the touch interface, or you could put it on an interrupt so that you'll be interrupted when there is a touch information, then store it somewhere, and then your main application can access it there, and there'll be a continuous flow of data from it. That's what you'd want to do. In any case, but this is good for a test to see whether the underlying code is working. So let's have a look now if we can compile it. Now, in order to do that on this particular device, I think I showed it last time, but let's look at it again so that you understand. The way that this thing is set up is that obviously there is a switch here to turn it on and off, and there is a reset button over here. And in order to put it in a mode for it to download the actual code, you have to push the little button in there. If I can find it. There it is. Then you hold down the trackball button, which is actually GPIO 0 switch. And you can then release the reset and then release the trackball button. So now it is in a mode where it's waiting for it to upload the code. So we can actually go back to the display, and we can hit this little button over here to actually upload. So it's going to compile. You'll also notice that Platform IO is much faster than the Arduino IDE, which seems to take forever to compile. So that is uploaded and it says success. So now we can actually have a look how it works. So what you have to do is after you upload it, you hit the reset button again, and there it goes. Initializing battery voltage 4.1 volts. It's connected to the IPC, so obviously the voltage is full voltage. So now, if I touch the screen, as you can see, it comes back with the touch points wherever you touch it. And if I touch it at the top there, it clears it. And if you move the stylus, you can actually, that's the 100 milliseconds, you know, the gaps that you see there. If you move it very slowly, you don't get any gaps, but it is only displaying the little tip of the asterisk. Anyway, it is working fine, as you can see. So far so good. Next episodes, we're going to hit some of the other bits and pieces in there. We've still got the trackball to go, the keyboard, the microphones, the audio out, the SD card. And in fact, the last thing we'll be doing is also there's an LVGL, which is a system to actually create graphical user interfaces for these displays. We'll be looking into that as well. So in any case, I'll see you guys later. Don't forget to like and subscribe and hit that bell button, and so that you'll be notified for the next episodes. And also make sure that you look at the description. In the description there will be information where to download the code and everything else, and information on the actual device and so on, where you can find that. So that's it, and I'll see you guys later.